forgot my microphone today, so you're just going to have to listen closely. And so today, at the 6th week, we're kind of taking a little bit of a thematic shift in the course. Some students have complained that it feels like it's two different courses, and I might say I kind of agree in that, the first half of the course was very much focused on R programming, using some of the packages in R's and those tools there, okay? The second half of the course will now move into computational statistics, which kind of from a big picture perspective is the idea of using the computer to answer questions related to statistics or related to probability that are too difficult to answer using traditional math. Okay, so what I mean by traditional math would be things like algebra and calculus and those tools, and solving things using equations and variables and getting an analytic exact solution. Sometimes the math there gets really hard, and so we say, well, can we get an approximate answer using the computer? And most of many times the answer is yes, we can get an approximate answer using the computer. And when we do get approximate answers using the computer, we'll use computational statistics for that. Okay. A big thing that we have to keep in mind, though, is that the way the computer handles numbers and math is very different from the way us people handle numbers and math. Okay. And so today's lecture will be on floating point precision. In last class, I didn't get as far as I wanted to, so I might have to continue on Wednesday. We'll see what happens. Okay, so today we'll talk about floating point precision here. Okay, and so here we have, we're going to model this after the, well, not model, kind of the standard that was developed for the way computers handle decimal numbers. So floating point numbers is used for decimal numbers in the computer. Okay, so decimal numbers in the computer use floating point. You also have integer values, right? And we know of these different types because when we look at a number in the computer, we can say type of, and it will say integer, or type of double. When they talk about double, they're referring to what's called a double floating point precision number, or basically a number with decimals. And inside the computer, all of this stuff is implemented at a hardware level, okay? So pretty much all of your computers probably use Intel chips. Maybe some of you have an AMD chip, but AMD and both Intel have implemented this IEEE 754 standard as far as the way numbers are being implemented. But I guess back in the 70s, there were different chipset makers that might have used different ways to implement the storage of numbers. But today, it's pretty much all following this standard here. And so this is done at a hardware level. So it doesn't matter if you're using R or Python or C. The way the numbers are handled inside the computer and stored in memory is going to be the same, okay? And the only difference is that R only allows for integers and double floating point, whereas C allows for single floating point precision and double floating point precision and things like that. And like Java allows the long, I don't know, there's different number formats for different programming languages, but as far as how the system is implemented, it's done like this. Okay, and so let's just talk briefly about binary numbers, and I imagine most of you have had some kind of exposure to binary numbers, but just in case we haven't, let's say we want to represent the number 5 in binary. We would have something like this. 5 is equal to the sum of we have to think of powers of 2, and so 5 is equal to 4 plus 1. Okay, so 4 being a power of 2, and 1 is a power of 2, and that it is 2 to the 0. Okay, so this number, the 4 is 2 squared, and the 1 is 2 to the 0. Okay, and so to represent this in binary, we would say this is 1, 0, 1. This number, the first one is 2 to the 0. This is 2 to the 1, or the 2's place. This is 2 squared right here, okay? And so this would be 4 plus 0 plus 1, and we would have 5. All right, so that's binary, and we can count using binary. And then if we wanted to have fractional values in binary, that's also possible. Okay, so we have fractional binary values, and so we could have something like 1, 0, 1, and then I'll put a dot here, and this would be our, not our decimal point, but our binary point, okay, because now we're in the binary system. And so if I do 101.1, what is this value? So the 101, this part, this is 5, right? And then we are one position after the binary point, so that would be the what place? Not the tenths, not the hundredths, but the halves place, right? So this is the halves place. This is 2 to the negative 1. So this would be equal to 5 plus 1/2, or 5.5 in decimal. Okay, so in decimal, 0.5 represents 5/10. Okay, and then if we have more numbers, okay, we could do this. We could have 101.11. So this would be the halves place, half, and right here would be what? The quarter place. And so what is this value? Five plus 1/2 plus 1/4. So that's 5.75 in decimal. Okay. All right. But this is not actually how the computer stores values. Yes, we have to understand binary first, but the computer doesn't just say, okay, well, you know what, I'm going to just turn things into binary, and then I'm going to store this binary number, okay? Because if we think about the real number line, how many numbers exist between 0 and 1? There's an infinite number of numbers, right? And for any spot, we can have an infinite number of trailing decimal places or trailing digits after our decimal or binary point or whatever we're talking about. We can have an infinite number of things, and we don't have an infinite amount of memory. We might have 32 gigabytes of RAM or 16 gigabytes of RAM. We might have a lot of memory, but it's still not infinite. And so when the computer engineers were saying, well, how are we going to store numbers? They said, you know what? We are going to use this many bits to represent a number, and that's going to be a finite number of bits. Okay? And so in floating point numbers, we are using a finite number of places, a finite number of binary positions, or you can, in your head, it might be easier to just think of a finite number of decimal places to represent basically an infinite number line, right? So we're trying to go from the real number line where there's an infinite number to just a finite amount of numbers. And because of that switch from infinite precision to finite precision, a lot of our sacred and cherished rules of math no longer apply. Okay, so probably, I imagine in elementary school or junior high or whatever, you learned all of these rules of the numbers, like the associative property and commutative property and all of these things, right? And these were things that said, like, when you do multiplication, you can multiply numbers in any order and you'd get the same result. Or if you have parentheses to group your numbers, you can group them any way you want. Okay, I mean, like, if you do A times the group B plus C, we said you can do B plus C first and then multiply by A and get your answer. Or you could distribute that A and do A times B plus A times C, and you'd get the same answer, and it doesn't matter, right? And these are all true in real numbers. But when we're dealing with finite numbers and floating point precision, those things are no longer true. If you multiply by a third, and then if you do some stuff, those rules of algebra and those things, they no longer are true, and that can be problematic, or that could cause problems if you weren't expecting that. Okay, so let me just kind of give you a one slide nutshell of the problem with floating point. Okay, so the quote, and I put problem in quotes because it's not really a problem, it's just this is a consequence of what it means to be dealing with floating point numbers. Okay, if you're not dealing with floating point and you say, well, we want to represent infinite numbers, then you need an infinitely capable computer, which is not capable. All right, so the problem of floating point. All right, so I'm going to go to a decimal representation because I think we're a lot more familiar with decimal representations. But let's say you have a calculator and it only shows 8 digits on the screen. Okay, so let's say you have a calculator that uses calculator with 8 digits. Okay, now some of your calculators might be smarter than this, but let's say on your calculator you type in 10 divided by 3. What is your calculator going to output? Yeah, 3.3333333, right? 1, 2, 3, 4, 5, 6, 7. Yeah, so we've got a 3 and 7 threes after the decimal place. Okay, so you hit equals, this is what you get. All right, what if we take this and then I say, all right, let's multiply that by 3. What am I going to get? Well, depending on your calculator might be smart enough to know this, but if the problem that we would encounter is that this would be 9.999999. Okay, it's no longer 10. So 10 divided by 3 times 3 is no longer 10. It's something a little bit different. Okay, and the problem is that in the calculator, when you have this, it's that with finite representation, ten over 3 is equal to 3 and, what is this? 3,333,333 10 millionths. Okay, so this would be 3.3333333 exactly. So that's 3 and 3,333,333 10 millionths, and 10 over 3. Those are exactly equal with finite representation, and there's no way to differentiate between the two. And so when we say, what is this times 3, it's going to give us this value. And that's effectively the problem. Okay. With binary, with a binary system, we can represent numbers like 1/2 and 1/4 very easily, no problems there. But representing numbers like 1/10 or 3/10 is actually going to be something like this, where we've got an infinite series of kind of repeating digits that just eventually have to be truncated, okay? Because we can't use an infinite number of memory. We have to say, oh, we're only going to use this many bits. And so that it gets truncated, and so values like, so in binary, values like 0.1 or 0.2 have, infinite representations. Okay, so they get truncated, and are not exactly equal to 0.1 or 0.2. Okay, so there you don't have exact representation here. So we can try this out. You can go onto R, and you can type in options digits equals 22. Okay, because I think the default is options is digits is 16 or something. But you say options digits equals 22, and we would get something unusual here. Well, first of all, let me just say this. Here I'm going to write. Let's clear everything out. Okay. Or actually, here I'll turn back my options to digits equals 16. This is what you might have, and you have. If I do 0.1 plus 0.2, it says it's 0.3, right? And so I can say, you know what? Let's store 0.1 plus 0.2 and store it into A, right? So what is A? A is 0.3. But then if I say, is A equal to 0.3, it says false, okay? And this might be surprising, because we would say, well, 0.1 plus 0.2, is that equal to 0.3? And R keeps telling me that is false. It's true. 0.1 plus 0.2 is 0.3. I'm not playing a trick on you. But in the computer, these two things are not equal. And so we can dig in, and we'll do options digits equals 22, and this might reveal a little bit of what's going on. Okay, so if I say 0.1, we see that it's not actually 0.1. It's something that's very close to 0.1, but it's not exactly that, right? It's just like, because we're, again, 0.1 in binary has a whole bunch of trailing binary digits. I don't know what it is off the top of my head, but it's a bunch, and it gets truncated, and so the truncated representation ends up looking like this. Okay, 0.2 in binary is its truncated representation is actually this in decimal value, and when we do 0.1 plus 0.2, we get something that's very close but not equal to 0.3. And if we ask what is 0.3, well, in binary it gets represented this way, as something very close but not exactly equal to 0.3. And so so this is why when we say is this number 0.1 plus 0.2, is that equal to this number, the computer says no, they are not equal, right? And that's because the number that we are looking at in binary is not the actual number that's being represented. And so if you're expecting kind of our regular rules of math to hold up, that's not going to work. So one workaround of this is using all equal. Okay, all equal understands that the computer is not super precise, and you can say is 0.1 plus 0.2, is that equal to 0.3? And it will say true. Okay. But it's, again, but if we did all equal, 0.2999, is that equal to 0.300? Something like this. It says true, okay? And so it's just saying, are these two values, are they close enough to each other? And all equal will say true. You can't use that to try to prove something mathematically, right? Like if if you were trying to use, let's say you were struggling somewhere in some math class and you wanted to use the computer to prove that two things are equal, that's not going to work, okay? Because at you know, some floating point representation, it's not exactly equal to each other. I think, yeah. So this is what we have, right? Obviously, if I asked you, is 2.99999 equal to 3.00004? The answer is no. That of course, they're not equal. But to the computer, if you ask all equal, which says, you know what, are they pretty close? It'll say, yeah, they're pretty close. Okay, they're close enough, but they're not exactly equal. So this is kind of the issue that we have going on here. And depending on you know, the way we do functions here, 10 divided by 3 gives me this. Let me do 1/3 times 10, and we're getting different answers here, right? So these are obviously in real math they would be exactly equal. In computer math, they are not, and so we have to keep that in mind. Okay, so we'll talk about how computers are kind of represented in the system here, and so we'll talk a little bit about the system of floating point. This is the IEEE 754 system. Okay, so but that's the problem of floating point numbers in a nutshell. We're using a finite representation for something that's potentially infinite. Okay, so we learned about type double, and so if we look at a double precision floating point, this is what it is called. The computer will use 8 bytes or 64 bits to store a number, okay? 64 bits to represent a number, right? So this is about equal to having a calculator that has 16 digits to represent a number, okay? And so for most purposes, having a calculator with 16 decimal places of precision is pretty good for most situations, but that means if you needed that 17th or 18th decimal place, it's not going to be there for you, okay? You can't rely on that. And so so this is what we have: 64 bits to represent a number, about 16 decimal places, something around there. Okay. All right. Those 64 bits are split into 3 portions. Okay. 1 bit is for the sign. So 0 for positive and 1 for negative values. Okay. Then we have 11 bits for the exponent, and then the other 52 bits for the mantissa. Okay, the mantissa is the part that's not the exponent. And this is how numbers are stored in the computer, again, implemented at a hardware level. And to kind of give us the idea of how this works, I'm going to use something called a mini float. All right, so it's the same idea here, except instead of having 64 bits, we're going to have the mini float will have 8 bits, okay? And the 8 bits, we will have 1 for the sign, 3 for the exponent, and 4 for the mantissa. All right, and so we will get the same kind of idea of how these double floating point precision works, except so I'm going to split up. Whoops, something happened. Okay. We have the exponent here and the mantissa right here. Okay, so same kind of idea here. All right, let's say we want to how do we store the number 5.75 as a mini floating point? Okay, so this we want store 5.75 as a mini floating point. Okay, well, let's try this out. What we're going to do is step 1 will be 5.75 into binary. Okay, so into binary, this would be, the 5 would be 101, and then the 0.75 would be 1, right? We get a half, we get a quarter, 101.11 as binary, okay? So step 1 will be putting this into binary. The next will be then to put this into scientific. Okay, so what is scientific notation? Scientific notation normally in decimal system means you have just 1 digit in front of the decimal, and then you have everything else, and then you say multiplied by 10 to the some power. Okay, that's scientific notation. Okay, we're going to have scientific notation in binary. So basically, we will have 1 digit in front of the decimal, so that will be 1 point, and then everything else goes behind the, not decimal, behind the binary point. So now I have 1.0111, and we would multiply this by what? By 2 to the, because we moved it over 2 spaces, we would have 2 to the 2. All right. Or if we wanted to be pedantic about it, we can say multiplied or times 2 to the, in binary, 2 to the 10, okay? It's 2 to the 2, but it's a binary 2, right? Okay, so that's what we have here. And if we convert everything into scientific notation, then that means there's always going to be 1 number before our binary point, right? Even if it's a small number, you just move it so you get 1 number in front of the binary point, and then you have everything else. And because we're in the binary system, we know that the number in front of the binary point has to be what? It has to be a 1, right? You can't have a 2, you can't have a 0, it's got to be a 1. So if we take a number and we convert it into binary and then put it into scientific notation, the number in front of the binary point will always have to be a 1. This will always be a 1. So this allows us to kind of ignore this value and just keep the things that come after the binary point for our mantissa. Okay? So what we have so far is that this number, our sign is 0 because it's positive. And then our mantissa is going to be 0, 1, 1, 1. Okay? These are the 4 digits after the binary point. So we're going to put those into our mantissa. Okay? We have to do something special to the exponent though. Okay? So we would raise it to 2 to the 2, but we have to do something special to the exponent. So I'm not going to just say, I'm not going to just write 0, 1, 0. That's what I would do. If I didn't have to do anything special, I would say, well, we're raising it to the second power. 2 in binary is 0, 1, 0 using 3 digits, and I would put 0, 1, 0. But we have to do something special first, and that's what I'll do on the next slide. Right? But is this okay so far? Okay, so what do we have to do that's special? Well, with scientific notation, we can have that that exponent portion can be positive or negative, right? So we can represent very big numbers by saying, well, we've got like Avogadro's number 6.022 times 10 to the 23rd, a very big number, right? Or we could have something very, very tiny. I don't know what the Planck constant is, but it's some number times 10 to the negative something else, right? And so scientific notation allows us to represent very big numbers or very small numbers using either a positive or a negative exponent. So again, in our floating point, we've got 1 for the sign, we've got 3 for the exponent, and 4 for the mantissa. So for our exponent here, we want to be able to represent both positive and negative numbers. Okay, so we need to represent both positive and negative values. Okay, so we have 3 bits. So how many values, unique values, am I able to represent? 8, right? 2 to the 3 is I can represent a maximum of 8 unique values. All right, and so with 3 bits, those unique values would be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. These are the unique values. So normally this would just be 0, 1, 2, 3, 4, 5, 6, and 7. Okay, these are the values we could represent. However, what we're going to do in order to say we want both positive and negative values is we are going to add a bias. Okay, so this is called the biased scheme. Biased scheme for integers technically is what we do. And we just say, okay, you know what? We want about half of these numbers to be negative and half of these numbers to be positive. So what I'm going to do is I'm going to say, you know what? If I see 0, 0, 0, that's going to be -3. This will be -2, -1, and 0. This is what we'll have. And then we'll say this will be 1, 2, 3, and 4. So here we have a bias of 3. Okay, we've shifted the values down by 3, so we can represent both negative and positive numbers. Bias of 3. Okay, so we shift the values down. To represent both negative and positive values. All right, is that okay? So that's what we have. And so going back, what we had before was we had 5.75. This became 101.11, which became 1.0111 times 2 to the 2. And so in our mini floating point system, we said, okay, the mantissa, this part, comes down right here, 0, 1, 1, 1. Okay, it's positive, so we have a 0 here. And then this portion right over here, this 2, okay, 2 in the biased scheme is represented with a 101, right? And so that's what we will put in for the exponent part. So the exponent part, it looks like a 5, okay? But we have a bias of 3, so we shift that down and we say, okay, it's actually 2 to the 2. All right? So this is, with 3 bits, the bias is basically we want half of the values and 0 to be negative. We want half of the values to be positive and the other half to be negative and 0. So our bias is going to be 2 to the 2. It's we have 3 bits, right? So our let me just write this. Okay, so the bias for other floating points, like would be 2 to the n minus 1. How many, if you have n bits for the exponent, so in this case, 2 to the n minus 1 minus 1, all right? So we have, with 3 bits for the exponent, we have 2 to the 3 minus 1 minus 1. So this is going to be 2 squared minus 1, which is 3. Well, that's our bias here. Okay. In double floating point, for double floating point, we have 11 bits for the exponent. So what is our bias there? Okay, 11 bits for the exponent would be 2 to the 11 minus 1 minus 1. So it's 2 to the 10, which is 1024, minus 1, we have a bias of 1023. So, whatever number it is, you would basically shift that value by 1023 to figure out how to represent it in binary for the exponent portion. Is this okay? All right. So we have that. We have a few kind of special cases here. And so this is how we represent some values here. We have a few special cases, and then, and yeah, I guess I'll have to cover the rest on Wednesday. Some special cases. Okay, so the exponent, if the exponent is all ones, and the mantissa is all 0, then you have infinity. Okay, so in this case, if I have 0, 1, 1, 1, and then 0, 0, 0, 0, this is positive infinity. And 1, 1, 1, 1, 0, 0, 0, 0, this is negative infinity. So in our computer, when we're dealing with double, we sometimes get infinity and we sometimes get negative infinity. It's not actually infinity or negative infinity. This is just a representation for infinity or negative infinity in double floating point precision, or in floating point precision here, okay? And then if you have all ones in the exponent and something other than all zeros, in the mantissa, then you have it's not a number, okay? So that would be, something like you have 1, 1, 1, and then you have something other than all zeros. So this is not all zero. So this would be not a number in the system here, okay? Which means, technically, the largest value that's not infinity that can be represented largest non-infinity value would be 0, 1, 1, 0, 1, 1, 1, 1. Okay, that would be our largest non-infinity value in our thing. So what would this be? This would be equal to 1.1111 times 2 to the 110 is a 6. We have a bias of 3, so this is 2 to the what? 3. Yeah? Is that okay? Maybe I should write it this way. 6 minus 3. I don't know if that's any better. Okay. So this is our value here. So 1.11111 is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 times 2 to the 3, or times 8. Okay? And when we do this, we get 15.5. So in our mini float system, this is the biggest number we can represent that's not infinity. And if we go any bigger than this, it becomes infinity. Okay? So you're counting 1, 2, 3, you get to 15, 15 and a half, boom, infinity. All right? That sounds silly, okay? But that's how it would be if you had a floating point number where you used only 8 bits to represent your number. So floating point will always be either 32 or 64 bits. And in our systems, we all use 64 bits. And so the largest number we could represent that's not infinity with 64 bits would be something along the lines of 2 raised to the 1.111111 times 2 to the 1023. Okay, so if I do 2 to the 1023, I can represent that. Okay, and I can do 2 to the 1023. So that would be 1.0 times 2 to the 1023. 1.1 times 2 to the 1023 would be 2 to the 1023 times 2 to the 1022. Okay, so I can have that, and I can do plus 2 to the 1021, and I can keep going, and we would have these values would keep changing a little bit, little by little, okay, and we would get to a certain point, but if I cross over and I say, you know what, let's do times 2 to the 1023, if I add two of these together, then it says infinity, okay, because it can't handle a number bigger than 1.111 times 2 to the 1023 there, okay, so this is the pretty much, that's going to be the largest number we can get. You can type into your computer dot machine, okay? When you type in dot machine, it kind of shows you the biggest numbers we can get, okay? So the biggest number I can have is double X max. This is the biggest number I can have before it's infinity. This is basically about 1.8 times 10 to the 308. Okay, a little bit smaller than that. And again, we only have about 16 decimal places of precision. So you can't, if you take this and you say, what is this plus 1? Okay, it's going to say it's exactly the same thing, because you're basically saying I've got a calculator with 8 decimal places, and then, I want to add something that's, 300 decimal places away. It can't keep track of that, okay? So if we do this plus 100 or this plus 1,000,000, they're all going to just say it's exactly the same thing. It's just when you get a little bit bigger than this, it needs to at least register to register a change here, okay? So this kind of, the machine here, dot machine, will tell you all of these things. Okay. We'll see you guys on Wednesday, maybe, okay? And again, if you can go to Hadley Wickham's talk, I encourage you to do so.